Hello and welcome to this lecture. This is lecture 18 of the introduction survey to or of plasma physics. And if you've been following the lectures in their proper order, you'll remember that we have been talking about inertial confinement fusion. That is a topic that we unfortunately do not have the time to explore further. And starting today, we'll go back to a more standard set of topics. In particular, we are going to start talking about plasma waves. And really, the way this is done in our textbook, which will follow for today, is that the first part of the chapter dedicated to waves in a cold plasma, which is the starting point for discussion of waves, that's chapter 4, actually talks, or doesn't talk, it's a book, describes waves in general. I'm not going to go through all of the material that's in the textbook, in particular in the first part of chapter 4. I am going to assume that most, if not all of it, is going to be familiar to you. And I'm just going to go through a couple of or three of things rather quickly so that we can be sure that we're all, so to speak, speaking the same language. And after I put a nice box around my plasma waves, maybe plasma, maybe not, my waves in general, now I'm going to ruin it. Okay. First thing we want to do is, well, remind ourselves of what Fourier transforms are and why the Fourier representation of waves is advantageous and relevant to our course. As it happens, as you have hopefully seen in other courses, actually stopping for a moment to talk about Fourier transforms is not complete waste of time, because you will remember that there are different normalizations that are used in the definition of Fourier transforms. At the end, that's really not going to matter all that much for what we're going to be doing, but it's good to be precise about what we're going to do. Now, our textbook uses tilde to represent the Fourier transform. And working kx space, the Fourier transform of some function of x is going to be f tilde of k. Now, I dislike that notation. I prefer to use a subscript f to indicate that something is a Fourier transform. The reason why I have a an issue with that notation is that when we work with vectors, the textbook uses bold characters. So it's going to be, no, it's not impossible. We could do it. Your handwriting, actually, it's pretty cool. I could just make this bigger. Say, okay, this thick V as opposed to thin V. So that's a vector. I think that's just going to be confusing. So I'm going to use vector signs for vectors, and I'm going to use a subscript F so I don't have a vector over a tilde or the other way around. Okay, that's my introduction of the notation. The Fourier transform, the way we're going to use it is defined as 1 over the square root of 2 pi of the integral between minus infinity and plus infinity. This is, of course, in one dimension of f of x times e to the minus I k x dx. And the inverse of this integration, which is the Fourier transform, is going to be the operation that gives us back f of x. I'm going to again have the factor 1 over square root of 2 pi. The integral is again between minus and plus infinity, but now I'm integrating the Fourier transform of f, which is a function of k, times e to the I k x in dk. Please remember the difference in sign, and notice that I've put the square root of 1 over 2 pi factor in front of both integrals, as you will have seen or heard elsewhere. A different convention is to just use the 1 over 2 pi in front of one of the two integrals. Okay, that is our definition of Fourier transform. You've probably seen how you transform a Gaussian. It's not really all that interesting for us. Now, as I said, this transform was defined in the space dimension. That is in X and K space. And I can do in the same thing in time dimension. That's going to be T and omega. And I can do both at the same time. Okay, what happened here? Moment of break to fix the font. I hate it when this happens. Okay, fixed it. I was saying that we can do the same in space and time, in particular in three-dimensional space and time together, not to say at the same time. And that is what is going to give me a transformation for general function of position r and t. Time, I'm transforming 4 dimensions, my square root of 2 pi becomes 1. Well, my 1 over square root of 2 pi becomes 1 over 2 pi square, which I'm going to do with a straight line. What happened here? Okay. Straight line. There you go. Here I have 2 pi square, and then I have 2, or rather, 1 integral in 3 dimensions of space and 1 integral in 1 dimension of time. That's, you only got 1. I'm going to indicate all the integrals with a single integral symbol. All the integrals tend from minus to plus infinity, and what I'm going to integrate is the Fourier transform, which is a function of k, it's now a vector, and omega times e to the, let's see, guess I have space to do it. All right, e to the I k dot r minus omega t. The sign comes from the definition of how we define the transform. Can do it either way. The k, the 3k, because I'm integrating 3 dimensions in k space, the omega. And I believe the symbols are sufficiently clear. I don't need to spend any more time on them. Okay, now the advantage of Fourier transforms that you will already know of from other courses is the following, that derivative turn into algebraic equations. In particular, partial derivative with respect to time okay, this thing is being silly today. I don't know what's going on. Becomes minus I omega, and derivative with respect to x would be I kx. In general, if I have nabla operator, it could appear in a curl or divergence or gradient. I'm going to transform that in an ik, where k is a vector. The difference in sign is not a mistake. It's due to the way we define the transform. It's customary to define this way. Then what we obtain is when we look at a differential equation in space and time for our function f, that will turn into an algebraic equation. And what we are going to obtain is some function, some expression d, which depends on ik and minus I omega, just to keep the signs and the complex space explicit, applied to the Fourier transform my function. This will have to be equal to 0. Since we're going to use them, let me just do a quick aside and re-emphasize how this works. If I have a higher order derivative, I just keep multiplying. If it is time, I just keep multiplying times minus I omega. It is space, I keep multiplying times ik. And just have to be careful about how I'm doing it. Minus I omega to the power n. Sorry, that's not a good notation. This turns into minus I omega. If I have del square, which is not so unlikely, well, maybe I should call this del square of f. That will turn that will turn into an ik squared times f, or rather times f transform. Well, the way I've written here, I need to put the transform function. And for other common operators, if I have divergence of a vector function f, that will, in Fourier space, turn into ik dot f transformed. And last but not least, there would also be the gradient, but I think that's clear enough. Seeing everything else, the curl is going to be turn into a cross product ik cross f transform. Okay, so that's what we are going to use, and the expression I have here is going to be what we call our dispersion relation. I don't know why we call it a dispersion relation, actually, because we can write that equation for waves that are not dispersing. So I don't know. I'm sure it makes sense, but that's its name, and I'm sure you've seen this before, and you know what it is. I am going to guess that you do not need an example, but just in case, to be safe, let's suppose we want to solve a very simple wave equation where we have second derivative of f with respect to x squared is equal to 1 over c squared second derivative of f with respect to time squared, where of course c needs to have the velocity, the dimensions of a velocity. It does not need to be the speed of light, it could be any speed, but it needs to be velocity. Wow, this looks pretty disorderly. So let me do it again. Better. I apply my Fourier transform in both x and t, and I obtain an equation that looks like this, taking everything to the left-hand side, minus k squared plus omega squared over c squared times f tilde. No, sorry, I'm using the subscript. I'm getting confused by the book. F transform is going to be equal to 0. This, of course, will work for non-zero f only if this is equal to 0, and this is indeed going to be my dispersion relation, D, which, as you can see, is function of k and omega. And the dispersion relation is going to be D equals 0, so minus k squared plus omega squared over c squared is equal to 0, and that gives you a relation between omega and k. Omega is going to be equal to plus or minus k and times c. Of course, you could write it as k is equal to plus or minus omega over c. It's the same expression, but that's how this is going to work. And in this case, if we assume we are assigning a value for k, we can calculate omega. That's the way I've written it. C is going to be given by the problem, and we are likely going to assume that it's constant. Well, it does not need to be, but in this case, I've treated it as a constant. If it was a function of space and time, I would have had to be more careful doing my transform. I would have some extra function of x when I do the integral in dx, if that velocity was a function of space. But in general, we're going to assume that it is not. And you'll notice that if we assign a value for k, we're going to get two solutions. Those are called normal modes. Those are the, in a sense, natural solutions in the system. And those are going to be waves traveling left or right, depending on the sign. And the phase velocity is going to be equal to plus or minus c. Now, that's our solution. Then once we know once we have this relation, we can go back to our inverse Fourier transform defined here. Maybe I can put a little box around it and replace omega with the omega function of k that we obtained from the dispersion relation. And then I only have to integrate in decay, because the integral in the omega is trivial. Nothing depends on omega. So I solve for omega as a function of k. And I can write my solution Let me write in a little more detail. Once we find omega of k, the solution now, this is not obnoxious. The solution of the original differential equation can be written as f of r and t. This is the general case, so I'm using a vector for space, is going to be equal to 1 over 2 pi to the 3 halves times, okay, here's where things become a little more complicated. Book uses alpha. Let's use alpha. And I'll define what this means. Integral over the whole space of f transform alpha, function of k. Notice this does not depend on omega anymore because I got rid of omega by finding omega as a function of k. And this multiplies e to the I. Let me make a little more space here. Come on. K dot R minus omega alpha, which is function of k, times t. And the integral is in d3k. I've already integrated over omega, because again, nothing depends on omega. Omega alpha is a solution of the dispersion relation. In the case above, I had two solutions, so alpha will be, I decide the one with the plus is the alpha equal 1, or the one with the minus is alpha equal 1, and the other one is alpha equal 2, and I sum over those. If I have 20, I need to sum over all 20. If I have 100, I need to sum over all 100 of them. Now, the reason why I do that is that, in general, the solution to my problem, once I apply my boundary conditions or initial conditions, or however my problem is formulated, will not, in general, be normal mode. But my equation is linear, and therefore I can use what's called the superposition principle and decompose the solution of my problem into a sum over the normal modes of the problem. I, again, assume that you've seen this before, and that this is not going to be a problem. Okay, now the dispersion relation that we got in the simple case we look at was a scalar equation, because we were dealing with a problem in one space dimension, and therefore f is in one dimension. This is not a vector. But in general, we may obtain a vector, and we may have a vector equation. And what happens in that case is that we are going to have a system of equations. We'll take the x component, y component, and then we do the transform. We actually have the kx component, the ky component, and so on. And what we need to do to solve the problem is to take the determinant of the matrix of coefficients for my equations, for the various components of my equations, and set it to 0. What that means is that we are looking at our system of equations and realizing that only if omega and k satisfy a certain relation, which is going to be given by setting the determinant equal to 0, I have the freedom to choose my solution in a way that's not only 0. So that's the equivalent to what we did by setting the term in square brackets that you can still see equal to 0. That was for one dimension. And in 2 or 3 dimensions, you have to take the determinant of a matrix. Now, the next thing we have in our textbook is a discussion of the group velocity, and in a way, that's also a discussion of linearization. I'm not going to spend the time to go through that. I very much hope that you're familiar with group velocity and how to do all these things. And what we're going to do is switch to the next section in the book and look at the general form of well, get back to plasmas, let's say. Oops, I lost my. That's why it keeps disappearing. Ah. Sorry, having technical difficulties. All right. Now we're going to talk about plasma waves. Okay. The first thing we want to do is write the starting point in our calculation, which is the general system of equations we will have to solve. And those are, I don't need a capital letter there, going to be Maxwell equations. Again, I'm going to follow the textbook. This is not quite the only way to do it, but this is pretty understandable, I hope. We'll see in a moment, or you'll see in a moment. The way it's done in the textbook is to define or differentiate between microscopic and macroscopic Maxwell's equations. That is, microscopic means as Maxwell's equations are used to describe the motion of a single particle. Macroscopic means how do we describe the properties of a material. And well, you're familiar with them, but we're going to use them. All right. Let's do some writing. Let's leave a little bit more space so I can put tags on them. So for the microscopic, okay. We have del cross B is equal to mu naught J plus general form epsilon naught mu naught d dt. And del cross E, it's a little messy. Let me clean it up. Is equal to minus dB over dt. Divergence of E is equal to rho 0 divided by epsilon 0. I'm sorry, rho. Let me use the same notation as the book. Rho sub Q. That's the charge density. Okay. And so that's the Poisson equation, and then divergence of B equals 0. That was the microscopic one. The macroscopic one is going to look like del cross H is equal to J sub R plus d dt. J sub R is the quote unquote real current. That is, well, let me finish writing and then I'll define. Well, the real current, quote unquote, is defined by dividing the total current between the actual current and the magnetization current. And that's going to depend on how you define your polarization charges. And sorry, magnetization currents. That's going to be a matter of definition. And I gave it away. I'm going to do the same thing for charges. So this part doesn't change, but for the Poisson equation, we're going to have rho sub R on the right-hand side, which is, again, the real charge. And while in the microscopic case, I had the total charge. And this, of course, also does not change. Now, let me put a couple of tags here. Which one is which? And And rho sub q is going to be the total charge density is going to be equal to rho r plus rho p where this is the polarization charge. And the book does not use specific symbol for the magnetization current, but same idea. The total current is the sum of the real current and magnetization current. Okay, now that's what we have to solve. And the way to proceed is to find well, first of all, to decide how you want to do it. Okay, but we need to find a solution of these equations that is find all the fields in a physical system. Therefore, what's going to be relevant to us is the macroscopic version of the equations. But we also have to be mindful of the fact that in that version of the equations, we have more vectors than we have equations, more unknowns that we have equations for. And what's missing is a relation between D and E. So I'm just going to type them. As bold, that's going to be vectors. And that's going to come from the microscopic description of the plasma. So what you do is assume some or assign some field, and then you solve the equation of motion for the particles, and that's going to give you velocities as a function of the electric field, which then you use to calculate the current, which then gives you a relation between the current and the electric field. Now, what we are going to do, this is an important step, and it's worth emphasize. We're only going to work with linear waves. What that means, what's a linear wave? It's not a wave that travels in a straight line. Linear wave is a wave that is described by linear equations. If you only have linear equations, then what we spend the first half of this lecture on, the Fourier transforms, are a really powerful tool. That's what we're going to use. And in fact, what you're going to do is obtain relations in or relationships, never know which one, in Fourier space first. Okay, let's review the sequence of steps. First, assume that the fields are given. That's all we've been doing about with single particle motion. The fields are given. I figure out how the single particle moves. Okay, great. Then take Fourier transform. And then solve for particle velocity. In Fourier space. Then, once you have the particle velocity, you can write the electric current density. Still in Fourier space. J is going to be equal to the sum over the species of density of each species times its charge times this velocity. V in Fourier space. And this I'm going to set to be equal to sigma dot E. So if the equations are linear, I can be assured that I can always do that. There is never going to be that I'm never going to find terms where I have E square and then I don't know how to treat them. That's going to be our conductivity tensor. Conductivity tensor. Okay. Once you have that, you need what you really needed. That is a way to connect E and D. Now, see if I can get, I think there should be a way. let me just say connect E and B. The logical step here is to realize that the equation relating E and D is going to be linear. And the reason is this is a linear system. I'm not going to have nonlinear equations. If that equation is linear, all I can have is that E is something times D, or D is something else times E. And in fact, the way this is written is going to be the in Fourier space is going to be equal to epsilon naught times capital K dot E in Fourier space, where K is some other tensor, and as it happens, it's also got a name. This is going to be the electric or dielectric, never know. This word here, tensor. Okay, so far so good. If this is confusing, good. Well, maybe not. But that's pretty normal. This is the logical sequence of steps, but I haven't quite told you how you're going to get there. And the way you're going to get there is from Ampere's law. So what you do is use the tricks that we've discussed. And you're, well, let me just do it. Hold on, I lost my pen. Just for a moment. Okay, sorry about that. I did find my pen that I just put down. Well, it does happen. Okay, so one thing I'm going to do is let's go back and look at our symbols. I'm going to set J sub R equals 0. This may be a little more subtle than we want to worry about. In practice, what that means is that I'm only going to worry about internal currents. There is no current applied from the outside. All I have is the sigma times E current, which is the current, as you see from the equation for J. This is the current carried by the particles in my plasma, and the motion of the particles in my plasma. So this is a pretty reasonable assumption. But if I do that, let's look again at our equations. What I'm going to have is I K cross B instead of del cross B. And here I'm going to be in Fourier space, so I'll try to remember to put down all the subscripts F. This is going to be equal to J, which get from mu naught J, which is mu naught sigma dot E. Mu naught sigma dot E transformed. And then I have the derivative with respect to time of E, which turns into a minus I omega. Just write it minus I omega epsilon naught mu naught times E transform. And this is going to go together with the macroscopic one, which is IK cross B. So same thing, del cross B. I set J sub r equal to 0. So all I have on the right hand side is the derivative of the time derivative of D, which gives you minus I omega epsilon naught mu naught K dot E. Well, then I'm done because, oops, Fourier transforms here. Because what I have on the left-hand side of these two equations is this, the same thing. Therefore, this is only going to work if the two equations are saying the same thing. Collecting pieces, I find that for these to both be true at the same time, K, which is a tensor, is going to be equal to the identity tensor minus, I prefer to put the constant in front, 1 over I omega epsilon naught sigma. And that's going to be our expression for the dielectric tensor. And this is pretty general. The only thing I've done is to assume the plasma behaves like a plasma. So if there is a current in the plasma, it's going to come from the motion of the particles. But everything else is pretty universal, as long as my problem is linear, which is all we're going to worry about for this case. Okay, we have maybe a little bit of time left. So perhaps we can start on the next step, which is look for a homogeneous equation in that is without any external sources for our plasma, and then we'll move to proper waves in a plasma. And I think we'll have to do this next time. Let me just leave you with the spoiler. Homogeneous, which is spelled with one M. by homogeneous, again, I mean without external sources. Okay, we'll leave it here for today, and we will be back with lecture 19 soon on these screens. Thank you, and we'll see you soon.